Engineers parked a floating city above a 3-kilometer trench, and not one chain touches the seabed below. Against all odds, the rig ignores currents, storms, and gravity itself. Here's how such a feat is even possible. Picture a structure the size of 2 football fields. Its steel skeleton weighs roughly 500,000 tons. That's heavier than the largest aircraft carrier ever built. Below it, the ocean falls 3 kilometers into blackness. No chain reaches the bottom. No anchor grips the mud. No cable ties this platform to the planet beneath. And yet, right now, dozens of these platforms sit motionless above the deepest basins of the Gulf of Mexico. They drill wells worth billions of dollars into rock buried under 1.5 miles of water. They house 200 workers, refine hydrocarbons, and burn flares against the horizon above an untouchable abyss. The seabed is unreachable, so what holds them there? The real answer begins with the sheer scale involved. 3,000 meters of water is not a number the human mind processes easily by any simple comparison. Stack 9 Eiffel Towers on top of one another, and you approach the distance from keel to ocean floor. Sunlight vanishes within the first 200 meters. Below that, crushing pressure would crumple ordinary steel like tinfoil. Temperature drops to 2 degrees Celsius. The seabed itself is a soft, silty plain older than most mountain ranges. Somewhere below sits a reservoir of oil or gas so valuable that entire national economies depend on reaching it. For decades, the offshore industry sought positioning the way sailors always had, with anchors, chains, and mooring lines. That approach worked in shallow water, 100 meters, 500, even 1,000. Past 2 kilometers, physics collapse. A chain long enough to reach bottom would weigh more than the rig it was meant to hold. Its own weight would snap it before it ever touched the mud. The very idea becomes absurd. Engineers needed a new phrase entirely. They chose dynamic positioning, because at this depth, an anchor snaps before landing. Now consider the forces trying to move this platform. Surface Gulf Stream currents push 20,000 tons sideways. Trade winds shove against every column, every deck, every crane, with the patience of a slow glacier. When a hurricane arrives, and hurricanes do arrive, lateral loads climb past 200 tons of horizontal force. That equals the weight of a fully loaded commercial airliner pressing sideways against the hull of this rig. The waves themselves lift and drop the entire platform through cycles of 10, 12, 15 meters of vertical travel. Through all of this, a fragile drill string runs straight down from rig floor to seabed wellhead. 3 kilometers of hollow tube, threading black water like a needle, held steady from the sky above. That drill string tolerates almost no drift. 2 meters of displacement and the pipe bends beyond yield strength. Any further and the metal cracks. A cracked drill string can rupture the well. A ruptured well means blowout. Blowout means Deepwater Horizon 2010. The Gulf of Mexico watched oil spray uncontrolled into the sea for months. So here is the contradiction at the heart of ultra-deepwater drilling. The largest movable machines humans have ever built must remain stationary within the margin of a parking space. They are massive, they are fragile, and unmoored. The first half of the answer is buoyancy, not the naive kind, but Archimedes' principle scaled to industrial extremes. Look closely at a modern semi-submersible platform and you notice something strange about its architecture below the waterline. The visible deck sits high above the water on slender columns. Below, hidden from view, are 2 enormous pontoons. Each pontoon runs the length of a city block, flooded with seawater to a precise depth beneath the surface. They sit 20 meters down, well beneath the reach of ordinary waves, because waves lose energy with depth. At the surface, the ocean is chaos. 20 meters down, the water is nearly calm, an entirely different world. By placing buoyant volume deep and connecting columns thin, engineers minimize what they call the water plane area. This is the cross-section of the platform that actually cuts the surface. Smaller water plane, smaller wave forces. The rig becomes almost invisible to the passing swell. It rocks gently where a ship would pitch violently. There is a second trick. The center of buoyancy sits deliberately below the platform's center of gravity. This makes the rig self-righting. Tilt it and physics pulls it back toward vertical. The design fights instability itself. Ballast tanks in the pontoons are continuously adjusted, pumping seawater from side to side in response to deck loads. The platform breathes. It shifts its own weight in real time to stay level against the shifting Atlantic swell. But buoyancy alone cannot hold a rig against the ocean. Here is where the naive answer completely fails. If mooring lines cannot reach 2000 meters and buoyancy only floats you, what prevents horizontal drift? The real reason is active, not passive station keeping. The rig does not resist the ocean, it negotiates, second by second, millimeter by millimeter. Beneath a modern drill ship, you find 6 to 8 enormous propulsion units. They are called azimuth thrusters, each a submerged pod containing an electric motor of roughly 5 megawatts power. 5 megawatts is enough to run a small town, and every pod rotates a full 360 degrees. They push in any direction at any moment with any combination of force the control computer demands. No human hand steers them. A control system reads the platform's position hundreds of times every second. Every 200 milliseconds, 5 times each second, the computer measures exactly where the rig actually sits. It calculates where the rig should be, subtracts the difference, and commands the thrusters to instantly compensate. The result is a machine in continuous conversation with the sea, listening and answering thousands of times. When wind pushes the deck northward, a thruster on the north side wakes up and pushes back hard. When a current shoves the pontoon eastward, 3 thrusters coordinate a synchronized westward counter against the flow. The rig is not anchored, and yet it stays put, constantly correcting itself, second by second, forever. But how does the computer know where the platform sits? This is the second layer of the miracle. The rig navigates by knowing exactly where it stands and uses several independent methods to remain certain. The primary reference is a differential global positioning system, or DGPS. Ordinary GPS is accurate only to meters. That is not enough for a rig with a 2-meter tolerance. So the platform adds correction stations. Combined satellite signals and ground corrections reduce the error to centimeters. Surgical precision on a moving sea. But satellites fail, signals fade. So a second system runs quietly in parallel beneath the ocean surface. Acoustic beacons rest on the seabed 3 kilometers below, emitting pulses of sound into the black water. Hydrophones on the rig's hull time each echo, triangulating position relative to the seabed with astonishing accuracy. A third system, a taut wire sensor, drops a weighted cable straight down toward the abyss below the rig. Any horizontal drift tilts the cable, and the sensor reads the angle. 3 methods refusing to lie together. Meanwhile, gyro compasses track the rig's heading to within 1/10 of a degree, constantly, unerringly, in every condition. Wind sensors on the highest deck measure gusts before they reach the hull, feeding predictive control models. Thrusters fire preemptively. The rig does not wait to be pushed by the sea. It anticipates the push. Redundant power grids feed the motors from separate generators on separate buses inside physically separated engine rooms. If one system fails, another takes over. If 2 fail, a third remains ready to hold position. The International Maritime Organization calls the highest tier of this design DP3, the platinum standard of dynamic positioning. It can survive 2 independent failures at once and still hold station above its target on the seabed. Yet a single software glitch could send this entire fortress drifting silently kilometers from where it belongs. In Brazil's Santos basin, the platform known as P-51 operates in waters more than 2,000 meters deep. Its sister vessels reach even further. Drill ships like the Stena IceMax handle ocean depths approaching 3,000 meters below. In the Barents Sea, north of the Arctic Circle, similar vessels drill through freezing storms and 10-meter waves. These are not laboratory conditions. These are the harshest environments on the planet, and engineering must survive them all. In 2017, one such platform in the Gulf of Mexico held position through a Category 4 hurricane's fury. The winds exceeded 200 km per hour. Waves reached 15 meters from trough to towering crest. Through the entire storm, the rig maintained horizontal drift of less than 1.5 meters total. 96 hours of continuous correction. 24 times per minute, the computer recalculated the world and adjusted thrusters. Not once did the drill string bend beyond tolerance. Not once did the wellhead lose critical alignment. When the storm passed, workers emerged onto the deck and the platform had not moved a single inch. This performance has a price. Running 6 to 8 thrusters at partial power consumes enormous quantities of fuel. The daily fuel bill for station keeping on a large drill ship reaches approximately $80,000 per day. That is $30 million per year spent purely on the extraordinary engineering task of staying perfectly still. It is among the most expensive forms of standing in place ever devised by human industry today. The number proves it. But here's the problem. What happens when the fuel eventually runs completely out? Step back and consider what the industry has actually built. The answer is not steel, not chain, not mass. The answer is buoyancy plus computation, physics plus code. Pontoons keep the rig afloat, thrusters keep it aligned, sensors keep the rig informed. Software closes the entire loop. The seabed a mile below becomes irrelevant. The old paradigm of restraint, tying a vessel down, has been replaced by a new paradigm of negotiation. The rig behaves less like a ship at anchor and more like a satellite whose orbit is liquid. Its gravity is the sum of wind, current, and wave. A philosophical shift is buried in this engineering. For most of maritime history, humans dealt with the ocean by resisting it. Anchors gripped, ropes held fast. Piers were driven into the seabed, but past a certain depth, restraint becomes impossible. So engineers began listening. They built machines that read the ocean's mood twice per second and answered back in real time. The human-machine loop has replaced the physical tether, and this same principle now shapes the next frontier. That frontier is already opening. Floating wind turbines will soon populate the deep waters of Norway, Portugal, and Japan. They borrow dynamic positioning technology directly from the oil industry, since they cannot be fixed to the deep seabed. So they float on triangular hulls, held in place by a combination of mooring and increasingly active thrusters. Lessons from the Gulf of Mexico now carry clean electricity towards shore through choreographed buoyancy and computation. Beyond wind, autonomous drill ships are already in testing. They carry no crew during transit, guided entirely by artificial intelligence. This AI learns the local ocean's behavior and refines its response over months of continuous, uninterrupted operation. Some designers imagine platforms working in water 10,000 meters deep, approaching the trenches near the Mariana. Others envision floating factories, floating desalination plants, floating data centers cooled directly by the frigid deep sea. All rely on the same principle: buoyancy for lift, thrusters for position, sensors for awareness, software for judgment. The climate itself is applying pressure. Storms are growing stronger, and hurricane categories, once rare, are becoming common. Sea states that once challenged rigs now define the design case for every new floating structure engineers build. Engineers are tightening tolerances, doubling redundancies, and rewriting control algorithms to handle a far more violent ocean. And they are preparing for a post-oil future where the same hulls and thrusters will host different missions, perhaps floating cities. Perhaps carbon capture stations, perhaps refuges for coastal populations displaced by relentlessly rising seas. The technology that once hid oil rigs from view may soon carry entire cities across the open ocean. What began as a narrow industrial problem, drilling for oil in impossibly deep water, has become universal. Large structures can now be placed anywhere on the ocean, regardless of depth. The seabed is no constraint. Water is no longer a barrier. The map of what humans can build has quietly expanded across the planet. 70% of Earth's surface is newly available, and most have never heard of the machines behind it. Subscribe to keep exploring. Ahead, more stories about how humanity quietly reshapes the boundaries of our world. The next time you see a photograph of an offshore platform on the horizon, remember what you're truly witnessing. Not a fixed structure, not a moored vessel, but a machine in constant invisible motion, correcting itself continuously. Holding position within a doorway's width, above an abyss deeper than most mountain ranges rise into the sky. It is one of the quietest miracles of modern engineering, born from a fundamental shift in human thinking. It works because engineers stopped trying to command the ocean and learned instead to converse with it. If these engineering solutions surprised you, this channel has more films on how humanity outsmarts nature everywhere. From tunnels beneath the Alps to bridges spanning impossible distances, the stories of engineering triumph continue here. If you want to see how floating megastructures will reshape the coming decades, the next film awaits. Subscribe now to continue the exploration. The next story of humanity outsmarting the